And so I want to talk about two things today. One is just show you what this incremental approach looks like, and then show how to layer JIT infrastructure on top of it. I think these are actually interesting independently. Some of you might think that the incremental approach is kind of worth knowing if you've ever taught compilers or taken a compilers course. And then the JIT stuff is pretty cool. Just a warning up front, this is based on one offering of my course, and I'm teaching it again this year, so I should be able to refine things. There's sort of a couple moments in this talk where I end up feeling a little bit like this. So just be aware that there's a moment or two like that in the talk. Okay.
When you say based on one offering, you mean because there is only been one offering?
There has only been one offering.
You're focused on a particular offering. Yes. Okay.
Yes. Yeah. Exactly. Yeah. One offering. Okay. All right. So what I want to do first is take you through what I mean by an incremental approach to constructing a compiler in a course setting. Okay. So up here at the top right, this is my entire grammar for my language. Expressions are just constant numbers. Okay. That's our sophisticated language we're going to start with. And I'm going to have a couple different data types in the compiler. I'll have instructions, values, and expressions. Expressions parsed to the expr type. Values are things that are directly representable in x86 assembly as values. So that's going to be things that are in registers, and in the case of this language, everything's going to be a 32-bit integer. And then instructions in x86 assembly. So in this case, the only instruction we're going to use for now is a move instruction. So when I say incremental, I really mean incremental, right? You can think of all the infrastructure you need to build a compiler for meaningful features. So far, we've got numbers and move instructions and references to registers. And actually only a single register so far. So to compile an expression, we're going to look at the expression. It's going to be a num-expr in this case, because that's all we have so far. We're going to have a vector of instructions, and we'll push and move of that constant onto it. And then we're going to serialize that list of instructions out into an assembly string. So the main here is just doing some parsing. I don't show the parsing, but we can parse numbers to strings just fine. Makes a new vector, and then goes through the work of getting the assembly instructions out. This result here is templating the assembly string back in, and we're going to print this out to a file. Just as a heads up, this is all going to be in Rust. You don't need any special Rust knowledge to understand anything in the talk. There's some cool things that come out of having done this in Rust, but I'll walk you through any code that you see. So along with this, we need a way, like this infrastructure here is going to make you like a .s file or an assembly string, and we need to be able to do something with that. And the little bit of, the tiny bit of skeleton around that, like the saying we're in the text section, the global label, and the return are going to be used soon. So to get this running, what we're going to do is we are going to write a Rust file. You can think of this as a C file. In Ghuloum's original work, he did this all in C, and so you can think of this as a C file with a main function too. I'm doing everything in Rust, but it would be this all works if you do it in C. And the Rust file has a main function that calls our code starts here, which is the label we've just made in its main, and prints out the result. And then there's a little bit of hackery at the top just to make sure that we're going to be able to link against that name in the assembly file. And then we use standard system tools for compiling and linking these things together. So the cargo run there just runs the compiler so that we get our source 37 into the assembly file 37. Then NASM is an assembler where we can get a .o file out of that .s file. AR just gets us to the right statically linked thing that rustc expects. And then rustc, you could drop in GCC here and it would work fine if you used a C main as well. Rustc compiles that Rust main that links against our code starts here to generate one binary that we run, and it prints it. All of this infrastructure prints the number 37. I want to pause here for a second and say two things. One, all the code for this is actually what's on the front page of the handout. The front page of the handout is the one without the QR code on it. So if you just want to be able to glance at that later, you have the example sitting there. And also just pause to let you take that in, and I'm happy to be like interrupted with questions just so that we understand the pieces of infrastructure here before we go on. So actually, why don't people just like, if you need to, like look at the sheet, like take a moment and like, let's just make sure we're okay before we go on, even talk to the person next to you. I'm gonna be quiet for like 30 seconds. Really actually quiet for 30 seconds for people to come up with any questions, or if they just want to smile and give me a thumbs up like everything's okay.
Can I ask you a question?
Yeah.
How come you get a 64 out, but you had a 32 over here? Where did the other 32 come from? So like you've got a 32-bit constant, and you're putting it in RAX, which is I think a 32-bit register.
Oh, that's a great question. So the constants are all 32-bit, but RAX is a 64-bit register reference. So
EAX would be the 32.
EAX would be the 32-bit register reference. Yeah. So basically, we do this to avoid a couple questions about encoding and overflow if our constants are the same size as our registers. But it's basically just a little hack to make the surface syntax easy. But really, we are going to be all working in 64-bit x86, and the values in our programming language that we're compiling will be 64-bit words.
Okay. Yeah. But the constants are 32 bits.
The numeric constants are 32 bits.
I have another question.
Yeah.
How come RAX is a value? What does that mean? What does that mean for a register to be a value?
It means it's a kind of thing that can go in argument position in an assembly instruction. So my inster and val types are a representation of instructions in my compiler. And the things I can put on the left and right hand side of an instruction, at least for move instructions and similar things like that, are these value things.
I see the val and inster now, which I hadn't seen.
Yeah. Yep.
Basically, operands of
the operands of the instructions, exactly.
So not value as the result of a computation necessarily, but value as a thing goes in.
It's the thing that's sort of fully evaluated in assembly, right? A register reference or a constant. Yeah. Now that I've had a conversation with Robby, any other questions from the room, or you can also just look at me and smile, or look at me and frown, or whatever you like.
Cry.
And you can ask questions if any came up. If anything is confusing, or I said something that's weirdly not defined for you. How many people have taken a compiler's course who are here?
Ages ago.
Okay.
Not valid.
Actually,
Okay. All right. So let's talk about growing our language. Okay. Growing our language from here. So we started with expressions are just numbers, and sort of our runtime representation of things that we can have in the, refer to during the runtime of the program are really like the current answer. That's about it that we had as our runtime system. Let's try and add binary operators. So this is going to be where op can be a thing like plus or minus or times. And then we can have two expressions that are the operands. So we're going to add that to our source language. This is the thing we are compiling. It's going to be in our source files that are the input to our compiler. Now we can write binary operators. And let's see what that's going to look like. So we're going to need new instructions, like adding and subtracting, like the add and sub instructions. We'll need new expressions to represent things like plus and minus. There's an interesting thing that happens when you have nested expressions, which is you could nest very, very deeply, right? We could have 5 or 6 nested pluses and minuses on either side of a plus and minus. And to evaluate those, we need some temporary storage space to help keep track of intermediate values while we're working on one side or the other. And so what we're going to do is we're going to add a parameter to the compiler called stack index that keeps track of how deep we are nested inside an expression. And after we evaluate the instructions for the left-hand side, we'll store them at a spot on the stack. Then we'll evaluate the instructions for the right-hand side, store them above that on the stack, and then combine the results together afterwards. And so this stack index parameter is going to track how deep we are inside a nested expression. In general, this is going to help us keep track of like how much space we need to evaluate something like a function body or something like that. So this is what we go through to add operators to the language, and then the new value we need to use as arguments for instructions is the ability to refer to things on the stack. So we need a memory reference. So offset is a memory reference from a register to with some offset. So this gives us basic operations and introduces students to memory. As a pedagogic point, one thing I've often noticed when I teach compilers is that by the time students get to compilers, they've forgotten everything about assembly. And so one thing that I'm trying to accomplish by using this approach is incrementally reintroduce assembly to students as well. So like first I remind them that they can have numbers and operators and registers. Then I remind them that memory and memory references exist. And sort of the incrementality of the compiler goes along with the incrementality of like reminding them how assembly works. So you'll also see that deliberately, the set of things that we use in assembly is growing with the set of, naturally with the set of things that we add in expressions. Next, we want to have a sense of binding. So we want to have an idea that we can have definitions of variables and uses of variables. So we're going to have let expressions. So let binds ID to the first expression in the body, which is the second expression. And expressions can now be IDs. And what we're going to do here is actually very similar to what we did for nested expressions, except we're going to have the ability not just to refer to the temporary values we just came up with for the left-hand right-hand side of a plus, but when we create a new binding, we're going to store that variable at a particular fixed stack offset, a particular spot in memory, and anytime we refer to that later in the body, we'll look at exactly that spot. So we add a new parameter to the compiler that's going to be the environment that keeps track of a mapping from the names of the variables. So the keys in this map will be the names of the variables that we're storing in a let expression to their offset on the stack so that we can look them up later. This actually uses all the same assembly infrastructure as binary operators, but adds this new idea of an environment to the compiler. So that gives us bindings. Finally, actually two more things that we need to add. So one is we're going to add if with true and false as new constants. We can add new binary operators like and or. And then we're going to have if statements that have three parts, the condition, the then, and the else. And we have a choice here. We actually have a pretty big choice. And the choice I tend to make is that we're going to come up with an interesting representation that distinguishes between Booleans and numbers in how we fit them into the 64 bits of a value. So we're going to make an interesting decision. This is actually the same decision that OCaml makes. I think Racket does something like this too.
Yeah.
Okay, cool. So you'll see that I put the least significant 4 bits in little brackets and sort of set them aside up here. And what happens is in this language, we make it so the least significant bit of every number is 1. And then we shift the number down by 1 bit. So that 32-bit number constant actually is shifted down by 1. So if you got the arithmetic representation or looked at this value in a debugger, it would look like it's 2n plus 1. Right? That 37 would look like 65. And then all Booleans are going to have a 0 in their least significant bit. And in fact, all non-numeric values are going to have a 0 in their least significant bit. And then we'll have specific representations for true and false, where there's a 1 in a specific spot for true and a 0 in a specific spot for false. We leave aside all of the least 4 significant bits because we're going to add more types later. And we'll use different bit patterns in that those last 4 bits to distinguish different types later. But
yeah. So Racket does what Shay does, whatever that is.
okay.
Old Racket wouldn't do this. It would just allocate true and false.
Okay.
And it'd be 2 pointers.
Got it. OCaml does roughly this. I know. So for what it's worth. Okay. And so then we need to add some stuff to our assembly representation. We need to be able to test if a value is equal to another value. So we need test instructions that'll take two arguments and check if they're the same. And we need to add branching instructions like jump to the representation and conditional jumps. JZ is jump if the last test was 0 and things like that. And so then we're going to have true expressions and false expressions and change what happens in num expressions for these new representations. And then another thing we're going to add, I didn't put the code for if here, the if is standard, but another thing we have to decide what to do about is what happens if you try to add true in a number, right? If I write plus true 7, what should happen? Something has to happen, right? And we pick that we're pretty dynamic here. And what happens is we want to check that in a plus, for example, both operands are numbers. So the code here is checking that the least significant bit of both of these is in fact a 1. And if they're not both 1s, then we give an error. We signal an error because we got a Boolean there somehow, and we don't want to get a Boolean there. So we'll give a dynamic error.
What is the reason for building in the types into the values? What's the kind of...
So, great question. So the question is, what's the reason for building the types into the values? 2 reasons. One is so I can do that dynamic check. Mm-hmm. And in part, what I'm trying to demonstrate to students here is that you don't need a type checker in order to have a pretty safe plus, mm-hmm. right? Like we don't have to do an implicit conversion or give up, right? We could have a reasonable, safe dynamic error. The other is later, I'm not going to talk about it in this talk, but later in the course we do garbage collection, and you really need to be able to extract all that tag information from the runtime values to do garbage collection. Mm-hmm. Okay, so that gives us this Booleans, but also this idea that values have different representations, and the idea of errors, which is a new thing. Finally, we add functions. I'm not going to spend too much time on functions, just as I'm seeing how timing is going and knowing that we have another excellent talk to get to. I'm not going to spend a lot of time on functions. The main point with functions is that we have a calling convention, and you compile the body and the caller, and there's a calling convention between them. Pending time at the end, I might say more about functions, but to make a couple of the main points I want to make, it's not worth going in detail into functions right now. So that is the high-level overview of what it looks like to do a compiler's class in incremental style. Every week, you have a working end-to-end compiler with some meaningful input language and some interesting output assembly, and you can run those programs end-to-end. The first couple days, it's just numbers. The next week you add the operands, maybe the bindings as well in the second week, then you add the Booleans, then you add the functions. And you get a progression through a course where every week you have a working compiler and it's a small diff on the old compiler. Okay. Questions so far? Yeah?
Yes, so what makes this approach just in time? I'm not sure.
So now it's a great question how we can incrementally add JIT infrastructure at each level, right? So this is how I taught my course until 2023. In 2024, I did what I'm about to show you, okay? So we had this as like sort of the day one, this is very close to the handout I give in day one of my class. We've sort of worked through it slowly over a couple lectures. You all get to work through it slowly over 12 minutes. So this is the infrastructure on sort of day one for the first compiler we have. And this is where I start brainstorming. What does it mean to do something just in time instead of ahead of time? Where's the ahead of time compiler here? It's right here. This is the ahead of time. Right? Like, I have to go and generate a binary once using all this infrastructure in order to run the program. We think about just-in-time compilers. They definitely aren't shelling out to NASM every time they need to generate some new code at runtime. So if we're talking about infrastructure and pieces that I need to do a just-in-time compiler, I better be able to take all this stuff and somehow do it in my, alongside my compiler in the same process, not as some other thing over here, right? So I'm not getting to some of the things some of you might think of when I say just-in-time compiler, like tag checking and optimization. It's going to take a couple slides to do any of that. But here's an idea. What if we didn't even have that right-hand side infrastructure, but we wanted to generate this code and then somehow evaluate the assembly code right away? So instead of calling our compiler, getting an assembly file, and then somehow linking the assembly file together using command line tools, we could call our compiler, get an assembly string or some representation of assembly, and then run the assembly in this process. Because that is the fundamental piece of infrastructure in a JIT. A just-in-time compiler, while the program is running, is going to collaborate with the compiler to get new machine code and jump to it. That is the fundamental operation of a JIT. We can talk a lot about like why you'd want to do that and how you do it efficiently, but that needs to happen. If you don't have that piece of infrastructure, you can't do any of the cool JIT stuff. So here's the idea. There's a wonderful library. This is something that is a reason I did this in Rust is it made it a lot easier to write the compiler and the runtime stuff that I'm going to talk about in the same language, which simplified a lot of the build process here. I used to do this in a mix of OCaml and C, and it's hard to make those things talk to each other in the way that I want to. So doing everything in Rust paid off here. That was actually one of the reasons I did this in Rust. So there's this package called Dynasm. It actually came out of the Lua world. It was originally a Lua package. But it is a dynamic assembler. So the way this works is instead of writing an assembly string, everything we used to do that was concatenating assembly strings is going to go through this package. And this package is going to let us give it descriptions of assembly, and it's going to give us back well-formatted machine code that we can jump to in process. So we construct an assembler, and instead of calling, this is where I called instructions to string before and got a string back that I templated into something. Here, I'm just going to call instructions to asm, and we're going to do some stuff with this assembler. And this is actually basically the same code I had before, except instead of giving you a string that says move the constant into RAX, I use this dynasm operation that says, you're going to take this ops thing, which Dynasm keeps track of and is going to use to build machine code. And I tell it, I'm going to give you some x64 instructions, and it's a move, RQ, reg to index, blah, blah, blah. This is just a helper that lets us go from, it basically evaluates to RAX from the point of view of Dynasm, but it indexes its registers by indices, and so we have to use this to get what was RAX. And then this is just dereferencing that number. So that's the same numeric constant that goes in there. So this turns into, when we run the program, move into RAX, the constant value.
So is semicolon like splitting out instructions, and is there macro stuff?
Yes, this is a macro. So dynasm bang is the indication that it's a Rust macro, and arbitrary syntactic quasi-quoting is happening that is going to the back end of dynasm that is keeping track of a whole bunch of state about like where labels are and things like that so that it can make good machine code. So Dynasm is a lovely piece of software that does a lot of things that I don't want to do. And the bang, the exclamation point here is an indication that this is a macro. So it like really manipulates the text that I typed here, and that text that I typed is not strictly Rust code. Okay, so then we add to Dynasm that we want to have a single return statement after all the instructions that we have for our compiled code. So we're going to have, our moves, all the calculations that we did before as instructions, and then a single return statement. And that's like our assembly string, except it's a special magic assembly data structure inside Dynasm now. And then we finalize the result, which tells Dynasm, do whatever you need to do to figure out any interesting like offsets or things like that that are going on in the assembly. And then we get a pointer to the start of that buffer. So start is the offset at the very beginning. So we're asking Dynasm, give me a pointer back to the very start of the code that I started generating. And so this will be the result of buff.pointer of start will be some real address in memory in this process. And at that address will be the machine code that corresponds to everything I stuck in that ops buffer. Yeah?
I'm lost with the ops.offset. Where does ops come from?
That was on the previous slide. It was like, get it from Danasm. Isn't it? Mut assembler.
That should say, no, that should say result.offset. I named it the parameter name from the function by mistake in my slides. That should say result.offset. It's the same value. Right.
Yeah.
Right. It's the same value. I just made a slide bug. Thank you. No, good catch. Good catch. That should say result.offset. Then we do this little bit of Rust ceremony, where in an unsafe block we say, everybody trust us, stand back. That address in memory, it's actually a C function that returns an I64. Right? Takes no arguments and returns an I64. And by the way, it uses the C calling convention. There's no arguments, so the calling convention isn't super important here. It's just a convenient way to get this to do a reasonable thing in many cases. But this ceremony is important, which is telling Rust, hey, this address in memory really is a function that's, if you call it, it will run code that returns an I64. And this is just a function pointer in C in some sense, right? And the function pointer in C is just an address to the start of the function's code, right? So we have to convince Rust's stringent type system what's going on, but that's what that code is for. Okay. So I claim that up to basic operations and memory, which is the stuff that, you know, the computational stuff like doing plus and stuff like that, we have successfully JITted week 1. Okay? Now what you can do is you can just run the compiler kind of in eval mode. You give it a source file, it compiles it to assembly, it generates the machine code in process, and jumps to it and prints the result. And we never had to invoke any of that command line infrastructure for Rust C, or have another wrapper file, or generate an intermediate.o file, or any of that. Yeah?
So you said in week 1. The thing we're looking at now is basically a new version of the course. It's not that you first teach everything using the kind of static compilation approach, and then halfway through the course you say, now we redo the thing in a
Good question. So what actually happens here is at the bottom of every assignment, there's a little, and now with JITs addendum, that's pretty straightforward if you've done the assignment. And the thing that happened in my first offering of the course is they started as required, and then they started to be optional as the course went on, because it was pretty challenging to continue to do all the JIT pieces. When I do this again next year, I want to try to figure out how to make this be even more integrated so this is not like turned into optional pieces.
But you don't expect to just do the JIT version.
Yeah, I thought about this. I may still decide to do this, but that's not what I did. My TAs didn't want me to do it because they said learning the ahead of time stuff was too important to stop doing. Because it's a good point, right? This is like a little weird if you're trying to teach the learning outcomes of a compiler's class with a .s file and stuff like that. Okay. So I have a question for you two, which is how long should I go? Like when should we assume people want to leave and stuff like that?
So my forecast was 45.
Okay, great. That helps me plan the rest. All right. So what I want to talk about next, basically I want to take you through, I'll skip the functions bit, which is the part that really makes me look like Charlie Day being a conspiracy theorist with the red wires behind him and stuff like that. I'll skip the functions bit. But I'll show you the assignments we came up with to push this JIT infrastructure through a few more weeks. So the next thing was bindings, where we introduced names. And this is where, like, as an instructional designer, I'm really trying to get kind of creative with, like, what can I do that is an interesting thing that is about bindings that also motivates a new JIT piece of infrastructure, right? Because we can obviously do the eval thing with a let, but, like, is there anything in bindings? Is there any other idea in binding names to values that I can sort of learn about JITs from? We're not going to do dynamic scope. So the idea we came up with was a REPL, like Python's interactive mode or Racket's interactions area, where you can define bindings one at a time. which is actually something that's kind of hard to do in an ahead-of-time compiled implementation of a language. How do you do a REPL for something that's implemented by compiling to assembly? Like, what does a REPL for C look like? Like, what does that mean if everything's always ahead-of-time compiled? So the idea is, let's have students implement this. Now, the compiler comes with a -I option that puts you into interactive mode. And there's a new statement declaration called define that lets you define a variable, and then in later entries in the REPL, use the variable. And so each time you see the greater than sign, that's like a prompt. So the user first typed define x50, pressed enter, got no output, then pressed +x3 and got 53, and so on. How can we implement this if the only tool we have for evaluation is compiling programs to x86 assembly? Right? And dynasm, right, which we just saw. So this introduces a really interesting idea that's important for a JIT to have, which is the idea that static information and runtime information can mix. Okay? It's a really important idea in JITs, which is that you're going to use information from the running program and mix that information in the next time you compile something. That's a pretty fundamental idea in a JIT. So we're going to have a new kind of thing to store in the environment. In the environment before, what we did is we just only in the environment ever had variable names mapped to a particular stack offset where they were stored. So the type of env before mapped from strings to spots on the stack. But now these defined variables, we actually know their value. We can run the right-hand side and get the value for that variable. And then in all the future REPL entries, we know what its value is. We just defined it, and we can fully evaluate the right-hand side. So now there's two options for what could be stored in the environment. There could be a defined variable where we know its runtime value already because we evaluated it. Or there could be a stack variable that's stored somewhere at a stack offset that we have from some nested let. Those are two things that we might have to keep track of in our environment. And so our REPL is going to be a loop that does everything I just showed you on the last slide. It compiles the expression, it uses dynasm to generate a function that we can call, it calls the function and gets a value back. But if the thing that we were just working on was a define, if the statement we just evaluated was a define, we are going to add that name, like X or Y in the example, to the environment with their value. Like the actual result value is going to be stored in the environment. So when we go to do variable lookups, one of two things will happen, right, in our compiler. We'll either compile a variable lookup to looking up somewhere on the stack, in which case it must have been a binding from a let that's nested somewhere outside where that variable is used, or it's a defined variable and we know its value. Yeah.
Is the hash map a mutable thing when you add to it, or is it?
That's a really good question. So here, this is, but it's really hard to tell. So REPL-env is a different hash map than the env. So the env is the thing that we use recursively as we go down expressions. And then REPL-env is a mutable hash map that's just going to be for keeping track of the stuff that's in the, that we've defined at the REPL.
So when you see X, how do you know if it's the X that's in a define versus the X that's in a...
If there's a let-bound X and a defined X, the let-bound X will shadow it because this one is an immutable hash map that will follow the recursive structure of the program. Okay, and so now there's this interesting idea. So that we have this REPL environment that keeps track of REPL defined values, and the compiler itself might carry some runtime values around in the compiler to use as information while it's compiling. And we can get an interesting thing to happen here where when we actually generate the instructions for these, we can directly inline like the value 50 for X. And it's actually 101. I just put the comment 50, but I was being faithful to the representation of 2n plus 1 here. But we can directly inline the value 101 for X in this plus expression and directly inline the value for 101 for X and 1801 for Y when we do the second expression. So we can literally take the values of those variables and stick them in like we had done like some kind of constant propagation or something like that, but it's from a calculated value. So the generated assembly here can directly inline known earlier REPL values.
Who does the divide by 2 and subtract 1 when you print out the numbers?
The print statement on the return from the cast C function. So you do the cast C function, you call it to get the answer, and then you shift before you print. Or if its tag is 0, you print the string true or false. Yeah. Yeah. So it's in main after you evaluate. So really, this should do it. Yeah. It's not in this code. Yeah. It should be right there where my cursor is. Where my cursor is, it should be. There should be a special print helper that checks the tag and prints the right thing. You're right. The code as shown is abbreviated and would print 101.
Okay.
Yeah.
Got it.
Yep. Okay. Cool. Okay. Okay, boom, did it. Everyone always jumps up and cheers when I do that on this guy. So here I claim that I've introduced one new good JIT idea, which is mixing mixing static and dynamic information in the environment of the compiler, and implemented something that's pretty non-trivial for an ahead-of-time compiler, which is to get this interactive mode. So the last thing I want to show you is like sort of actually the payoff of a JIT. The real payoff actually comes when you get to functions that might do these operations thousands or millions of times, but I can show you the infrastructure you need to do some optimization now. So remember this test that we added to all plus expressions to make sure that we weren't adding a Boolean and a number, or two Booleans, to make sure that the two operands to plus were always numbers. We added this test. It would be nice if we could remove those if we knew that the values were both numbers. And the new runtime environment that keeps track of runtime information plus static information has that information now, sometimes. If it's a defined variable, we know if it is a number or a Boolean in the compiler. We know that before we do any compilation. And so we have this end val business that we've updated in our environment.
What if I define it later again?
So far we don't have any problems with multiple definition going on because later defines will just override earlier defines, and we don't have functions yet.
But they could change the number to a Boolean.
Mm-hmm. And then the REPL end would change, and then future uses of that variable would reflect the updated.
Oh, you said we
REPL
don't
end.
have functions yet. So
Yeah, we don't have functions yet.
Okay.
So, yeah. And when we have functions, we disallow forward definitions, and so it works out for a while until we introduce variables, and then we're sad. But we box them, so it's okay. Yada yada. All right. So we had this
pedagogy question then. Like,
what's that?
A pedagogy question.
Yeah.
Like, could this be something that students could uncover, and you know, would that be interesting?
Probably. So keeping the REPL running while you add every feature for the rest of the quarter turned out to be like the biggest challenge.
Okay.
Right? That was actually really hard. And so yes.
They did discover.
They did.
I see.
They discovered things.
This was the madness of the functions pictures.
Yes.
Related to this?
Yes.
Okay.
But what we can do now is if we know that, let's say E1, the left-hand side of the plus, is an ID, and it's a REPL val, so it's one of these known defined values from the REPL, and its tag is number, and then it counts as a known number, and we can do the same thing for E2. And if either of them is not a known number, then we have to have this test. But if both of them are known numbers, we can simply omit adding this instruction. And so if both are known numbers, and you could make these tests more complicated to handle more cases, but if both are REPL vals and we know that they're numbers from earlier runs, we can omit this check. And now we've actually saved an instruction because we have this new kind of information, which is like what JavaScript engines are doing all the time. They'll omit certain kinds of safety checks in versions of functions that they compile with known types. Right? This is sort of the reason you put a JIT into like the JavaScript engine in your browser, is to make it faster when you encounter specific lines of code again that use the same types. So this gets us to something that feels like a real JIT payoff. And if you can do this inside functions, which is the thing I'm not going to talk about because it makes me look like Charlie Day, if you can do this inside functions, they get called millions of times. Now you can actually measure a payoff, right? You can't really measure a payoff at the REPL so well because this is pretty small expressions. But you can see that the instruction is elided when you get there. All right. So let's skip over the functions, although show you how crazy it is. There's like code that rewrites itself and stuff. Okay, yay, functions. And non-trivial, and the grad student who worked on this told me, Joe, don't tell a Rust audience about this without putting this slide in, but I'm skipping it. Okay. So the 4 phases that I usually do sort of to get the class going, and then I have a grab bag of other features I do after this, are sort of this starter, then bindings, then conditions and types, and then function definitions. That's usually half the class, and then the back half of the class changes a little bit depending on what I want to focus on. And my claim is, I've shown you ways to sort of get JIT infrastructure in a meaningful way layered on top of that stuff. I just have a couple things. So first of all, Mark was an undergrad TA. He's not looking for grad school anymore. He found a grad school, so I can't say that anymore. But he was great. Nico is going on the job market, though. He was the graduate TA, and he taught me Rust and did a lot of this work. And then Adianth was a master's student who took the course. This was a combined senior master's course. And he had the most complete implementation and told me I can share it with anyone I want. So his is the reference implementation for this now, because I just prototyped some of this up to the point where I knew it would work and then threw it at the students. And then his implementation is more complete than mine. So if you want a link, it's there. And Max New gets credit because he ported the original Camel version of this course to Rust, which saved me a whole bunch of time in getting started. If you want to revisit any of this stuff, the QR code on your handout goes to a web page that has a link to the course web page, these slides, and Adianth's implementation. So feel free to dig in.
So we heard from Joe. So you should think of this as like you've had the steak and potatoes of the meal. And you learned something serious about how you might actually use that for your own teaching or like learning possibly. And now we're going to have like a little sorbet. Okay? And it's going to be, okay, so like this is all my slides. Okay? All right, what I wanted to show you was something about a programming language I've kind of, I expect will have no bearing on your actual life ever, but you might enjoy learning about it. Because it's a very different way of thinking about computation. So that's what I'm going to try and do, is give you a little background about it, and then we'll write some code. Everybody with me? Is that okay? Okay, so Esterel. It's dates back. Anybody heard of Esterel before? Yeah. Okay.
Earlier than this week.
Before this week, anybody heard? So it dates 1983. Gérard Berry is a famous lambda calculus guy, and also like formed a company to use this programming language. Okay, really amazing. If you have a chance to meet this guy, he's amazing. He's an amazing person. Okay. And the language it's an imperative programming language. It has parallelism. And it has the ability to kill threads. Anybody ever heard of thread.stop in Java? Yeah, I know. Yeah. And what do you know about thread.stop? There's like one famous fact about thread.stop in Java.
Don't use it?
Don't use it, exactly. And that's because they can't get the implementation right. It corrupts everything internally inside the runtime system, roughly, if you try to use it. Okay, so this programming language, it's all good. Okay. The idea of combining combining work that you're doing in parallel with someone else is like a concept for combining computation. You know, like I'm going to do this part, you're going to do this part. We'll meet up later. Maybe we'll text back and forth as we go about it to communicate. This is like a fruitful way to organize ourselves to get things done. So why can't we have it in our programming language too? It's a similar fruitfulness applies there. Okay, so that's what Esterel is about. It's about structuring programs like that. Where you're thinking about the program as a kind of finite state machine.
So it's imperative programming in the sense that we care about programming with state change. Okay? It's not imperative in the sense that, oh, that's a bad thing because you can mess with someone else's state or something like that. No, it's like imperative has a good idea that comes with it that matches the way we organize ourselves when we're trying to get things done in the world. Okay? That's the thought behind it. So it's the same word. Okay? It's just like, let's see what positive things we can find with it. Does this make sense to people? A little bit? Maybe? I don't know. Okay. All right, so we're thinking of our computation as a set of state changes. And when you're programming with imperative stuff, you're programming state machines, you do the same thing, but it's not part of the programming language. Right? You can measure time in a computation. Anybody ever thought about like measuring time in a computation where you're not like using your clock or you're doing performance evaluation, but you're instead thinking, well, I changed this and I changed this, and sort of somehow you're measuring time kind of conceptually in the way you organize the program through that sort of state change, right? Not time for performance reasons, but time because like things are different now. It's the future, right? That's like state change. Okay, time. So that's what we're after here with by this notion of imperative programming. But normally you keep this in your head. The state change and what, it's like some pattern that you and your company or whoever's building the software has agreed that that's the way you're going to do stuff. In Esterel, you put it actually directly into the programming language. Okay, so you have this new construct in the programming language called pause. And every parallel thread has to eventually say pause. And the time between the pauses, you're calculating what the next state is going to be. And then when you hit pause, you've reached the next state. Okay? And so the idea is that you're going to interact with the world only in these pauses. And the computation takes sort of no time, but you're just figuring out what the next state is going to be. Okay? Okay. All right, let's see. Okay, so we should probably write some code to try to make this clear. So these things, if I might say the word instant. Okay? The instant is the time between the pauses. So we're just bringing the idea of the state change, making it explicit in the programming language. It's not like a programming pattern. It's not like we sort of agree that we're going to. It's like actually in the semantics of the programming language, and that gives us some power to avoid the kind of scary cocktail of parallelism, state, and thread termination. That's the first step. Okay, to make this like nice. Anybody do any functional programming? Do people like functional programming here? Yeah, it's like, what's nice about functional programming? It's because it uses functions, right? No, okay, good. What's nice about it? It's determinism. That's what's nice about it. It's predictable, right? I put the same thing in my function, I'm gonna get the same thing back out of my function. So that's what we're going for here. That nice predictability, understandability of the code. All right, but in this world, okay. So let's see. So the first thing I'm going to talk about is signals. And what we'll do is we'll write a traffic light, classic state machine kind of thing. So we'll spend the rest of the time writing some code. I don't know how many minutes I have, but the rest of them, 30 minutes, we're going to write some code and then we'll do it. Okay. So the first thing about Esterel, past instance, is that the state is always associated with something called a signal. It's like a variable. A signal is like a mutable variable that has different rules, so we give it a different name. Okay. So a signal can either be present or absent. So in the kind of simple case that we're going to start with, signals are like Booleans. Okay. They're either true, they're present, that's the Esterel terminology is present, or they're false, in which they're absent. The Esterel terminology is absent. And the reason they use present and absent is because the way that you set a signal, you don't say like red gets true. Okay? You just say emit red. Okay? Yeah.
So are those three different separate signals?
We've declared three signals. We've declared three variables, three signals. So think of the traffic light. Think of these are like if red is true, it means that the red light has got turned on. It's like connected to the wires inside the traffic light signal. So we've got sort of three lights we could turn on in the signal. And we don't ever want to turn more than one on. but they have three switches. So that's how we're going to put it into our program. And then so if you say emit red, that means that you set red to true. And if you just refrain from saying emit red, then red is false.
But you said there's never a way that more than one is true. So
Well,
then
no, we could have a bug. We could have a bug.
Okay.
Yeah, just in the same
That's
way.
not a bug. In Switzerland, that's actually correct. I'll have to show you outside.
You mean like it's green and then orange comes on temporarily to sort of indicate it's about to turn red?
Yeah.
Or maybe the other way around. Red's on and then orange comes on temporarily to indicate it's going to be. Actually, that's probably the way it actually works. Yeah, okay. Let's just do American traffic light. I don't know. we're only going to have one of these on at a time, okay? We're not so sophisticated in the United States that we can deal with it. Like that's like, which one am I supposed to look at? Oh my God! No, we're going to have this. Okay. So but everybody on so far with me. The rest of the constructs are, and the semantics overall will be something interesting and complex and different than what you're used to. But parallelism, state change, all these things are all familiar. It's just the particulars of variables is different. So you say emit red, that means red is true. And we didn't say emit orange, therefore orange is false. Okay. So, and then Esterel works, there's like something outside the Esterel program that says go. And then Esterel will run, all the threads will run until the next pause, and then we'll just stop. Okay, so to kind of bring that into the programming language, we need a construct that sort of sits outside our Esterel part, that says go. Okay, so the way you do that is you, pass it on again, is you say, let's call it R. This is the kind of way that we do that. So R is now a value in the kind of racket outside of Esterel, and that you can say, please go run one instant. And the way you say, please go run one instant, is you say react R. And it returns to you a Racket hash table whose keys are the signals and whose values are the values of the signals. So what this one is saying, I ran one instant in your Esterel program, and the signal red was set to true. So any signal that you don't see in there is false. And we may or may not actually see like a signal with false in here, but there's also a sense of sometimes you'll see like red false, but sometimes you just won't see red. And they're the same. They both mean red is false. There's some technical thing about whether the value was dependent on the actual computation about whether you actually see the false in there, but like it basically like every other signal in the world is false because and red is true. That's what happened to this one. And if we run another instant, then like nothing was emitted because there's sort of like a pause at the end of the program. There's like an infinite number of pauses now sitting at the end of the program. Everybody with me? Does this code make sense?
What would we have to do for it to be true, the red true, also after the second react?
Okay, let's do that. That's a great idea. Pause, we ended the instant, and then we say emit red. Emit red. So now if I do this, we get 1, then we get 2, and then we don't get any. So you run the first reaction, you got to all the parallel threads of which there was exactly 1, because that's what you start with, paused after the first react, and then it just kind of, the second react picked up from that spot and went forward, and if I put emit green here, then you'll believe that it's actually doing something different, and then Joe, let's let Joe speak into that. And it's going to be empty forever.
What happens if you take out the pause?
Any predictions?
Should be red and green at the same time, and then.
Yeah.
Okay, so the signals don't persist.
Right. So the signals is our state. Oh, and let's talk about the determinism. This is a good time to talk about determinism. So between pauses, what does determinism mean exactly? It means between pauses, all of the signals have a consistent. They are always they're set or they're not, and everybody sees the same thing. So between pauses, there's only one. That's the determinism. The signal is either set or not between any two pauses. In this one call to react. Okay. So it doesn't matter what you do. Everybody's going to see either red emitted or they're all not going to see red is not emitted. And I should put a little asterisk there because you can get a runtime error. Yeah.
So this implies we cannot have an instruction for unemit thread, for example.
Right.
Because otherwise, between pauses, we can have
right.
undecidable state.
If you choose to emit, then that's it. For the entire instant, everybody's going to see it as if it's there. Exactly. Yeah.
Can you emit threads in a looping way?
Yeah, let's do that. And I made some notes, so I shouldn't say no slide, but like have some idea about a good order to go in. And that's actually the next thing on my list, which is awesome. So we can say, here, let's see. Forever. Oops. And now if we do this, it's gonna go forever. Does it make sense? I made a little recursive function that okay, yeah. Yeah, that's a smile. That's nice. Yeah, it made sense. Yay. Smiles are fun. Okay, all right. I should also. Okay. Let me show you this thing I made down here. So you don't have to watch me. You can watch me type a lot, but not this one. Okay. So I made a little GUI. Okay. And just Racket makes GUIs. Dr. Racket's implemented Racket. It happens to have a lot of GUI stuff in it. But so this one, you pass in R, and you pass in a list of signals like that, and then it's actually calling React inside on the buttons. Okay. So when I click this 1 second button, it calls React once, and then just updates the GUI. So does it make sense, everybody? It's the same thing we were doing in the REPL. It just gets the hash table back and draws some. It'll be a little easier for us to figure out what's going on. Plus, it looks like a traffic light, which was what we were supposed to be doing, right? Okay, is everyone clear on? Yes, it's a non-trivial amount of code, like 100 lines or something like that, but it's not anything different than what we're doing in the REPL. It's just to be nicer to look at.
But I don't understand. Your original forever red code is still running. That's what drives the red light.
Oh, every time I hit run, we erase the whole world and start over again. Mm-hmm. And so it's not actually running. So what happens is when I click this 1 second, then the GUI callback for this button will call React, because you see the traffic light function got R as input. So it calls React on that thing, gets the hash table back, and then tells the GUI, okay, light up the lights differently.
Yeah, and 10 seconds calls React 10 times.
Yeah, exactly, okay. Exactly. So so I don't know. It's going to stay red for a long time, I think.
Yeah.
But we could do something like emit green pause, and so then we'll see green in the first instant, and then I click this, and now it'll turn red because now we've gone past that first pause, and then we're into the first red. That make sense? Yeah. It's just let's make it look a little nicer, kind of, okay, more programming, not interesting programming, not Esterel stuff. It's all outside of Esterel. So it's the world time is advancing, and it's, okay, everybody good? Okay. All right, now, so this is the, let's go back to this one. This is the safest traffic light, right? Right. So safety's nice, but maybe we also want to be able to go through the intersection. Right, okay. So this is where we get into the Esterel way of thinking. In Esterel, you don't, okay, so in regular programming, you would go okay, I'm just going to put an n argument here or something like that. That is not the Esterel way. Okay. The Esterel way is to kill the red one and start the green one when you're done. Okay. And Esterel has parallelism. So I didn't show you that. Let me show you. So you can say par, and then let's just do some kind of let's do this. Emit green pause green. Okay. So par means take the two sub-expressions inside the par and just run them in parallel in two separate threads. So what we'll get here now is we'll get red emitted forever. And then we'll also get green for the first two instance, and then after that, the green will go away. Does that make sense to everybody? So we just do it in parallel. So par just means do the two sub-expressions in parallel with each other. So it's literally spinning up Racket threads, and they just go independently.
So both threads go to their first pause.
Exactly. So both threads go to their first pause when you say React, and then you say React the second time, and they just both pick up from wherever their pause was. Yeah.
So that's why not having an unemit prevents any inherent race conditions, because you cannot emit and unemit at the same time. So since you can only activate a variable That means that even if they're happening separately, they can happen together
Yeah.
and have representation.
I'm not completely sure I'm getting your mental model and
For
answering
example,
it correctly, but
if I have an empty program
yep,
that is just pausing,
yep.
right? At this point, do I have red or not have red?
So
Like a program is just saying pause.
if I do this, for example,
No, I meant like in the par, forever red, begin, and then just pause.
oh, like here,
Yeah.
yeah. This will just be red. So that both threads. So there's one pause kind of inside forever red. So we'll get here, and then there's this pause. So both arms of the par will run to that. They're independent pauses, and then we'll only see red because
So
only
pause
one of
is
them
some
emitted.
sort of a synchronization step. And everything that happens until the first pause is represented.
Yeah. Yeah, you can think of it like a barrier. If you've studied like
Yeah.
OS or something like that, it's kind of like a barrier. But the semantics of Esterel are such that we have this whole thing going on with the signals that's like changes the whole world in kind of dramatic ways. But like intuitively speaking, you can think of like every thread is supposed to evaluate up to some finite amount of time and then call pause. And if they don't do that, it's a bad program. I don't have in Esterel from 1983. It'll actually check and be like, there's a way you can run forever without hitting a pause in this thread over here on line 7 and file whatever. Here I just treat I treat infinite loops the way infinite loops are treated outside of Esterel, which is somebody will hit the stop button probably when they get tired. But in principle you should be checking for that somehow and guaranteeing that if you want your Esterel program to work correctly.
What happens when this second thread in the par now, it has one single pause in it. So now we're at that point, and if you click 1 second, it's going to fall out of the pause. That second thread will terminate. Okay.
Yeah, exactly.
And then when all threads terminate, the program is finished.
Yeah, which never happens now because forever red never terminates.
Yeah.
Yep. And actually, in about 2 minutes, I'm going to have to explain that there's something much more complicated happening. So let me motivate that with an example, because that's exactly where we're going, is how does kind of the semantics of part. So if we want, let's do this. Pause, exit. So you guys know about exceptions? Like, or return. Anybody programming a language that has return? You can put that in the middle of the function, right? You don't have to put it at the end of the function. Okay, so there's a kind of a generalization of that idea where the part you return to isn't necessarily the beginning of the function. You can just put with trap, and wherever you put with trap, it like goes there. And normally that's kind of implicitly baked into every function. Someone write with trap and return is going to go there. But here in this language, you can just put the with trap wherever you want, and then exit will go there. Okay, yeah.
So it's the limited continuation.
Just escaping continuations.
Okay.
There's no resumption.
So it's like normal code CC.
Even less. It's like set jump, long jump. It's like just erase the stuff in between. We can never go back into it a second time. So it's like even less than that. So it can be implemented much more efficiently than full continuations. But it's like you use a continuation where you never call it outside the body of the argument you pass to call CC. It's like that kind of a restricted form in that sense. Does that make sense? It's much less powerful. It's just jump out. You never jump back in again later. Yeah, okay. Okay, so you say with trap T. Okay, so this. Let's just do 2 of them. So this. Oh wait, right. Yeah. Okay. Let's see. What this is going to do. We're going to in parallel. In parallel, we're going to run our forever red like we've been doing, I don't know for how long now. Then in parallel to that, we're going to do pause twice, and then we're going to exit. And you see, I put the trap outside the par. Okay, so we're going to just basically wipe out everything that's here, and we'll go to after the par.
So that kills the forever red thread?
It kills the forever red thread. Exactly. So this is the way that you express it in Esterel. But it's really, this is the way thread kill, you achieve thread kill in Esterel.
So I do exit without a trap, and that means that it's just within the thread.
You have to always you always have to say where you're exiting to. You have to, it doesn't have a, I mean, you can put these in where you want, but you have to actually like write it. Or you can make a macro. Yeah, so if we do this, we'll see a bunch of reds. Okay, that surprised me. Oh. Exit is the Racket function that exits the process. Exit trap is the Esterel function that exits to a trap. Sorry. So we were passing the status code T, whatever that means, to the underlying shell that ran our program. Never mind. Never back to Joe's lecture. Okay, sorry. Let's try that again. Exit. Okay, so we run this, and now the light turns off because we've basically now we're back in the end. We've gotten to the end of the program. That makes sense to everybody? So this thing is doing the forever red thing, then we pause, and then we exited the trap. So in this instant, the instant we hit this one, we're closing up the whole par, which means that there's nobody emitting red anymore. So that's why there's no lights there. So it's really like return here, except for we're returning from inside our par. So the other arm of the par is gone. Okay, and now we can do is, give me my mouse back, is right here we can do sustain, green. Okay, sustain, what is sustain? Forever red is actually called sustain, and you pass red in, okay, as an argument. So this is the actual Esterel name for forever red. Its whole name is sustain, and yes, I need to fix that part too, thank you. And it's got the infinite loop in it. It's the same thing. It's just called sustain, and you pass the signal in instead of like being hardwired to a particular signal.
So that's a typo in 68.
Sustain. Okay, got my arrows back. Okay, does that make sense, everybody? Yes, no, maybe so. So if we do this. Oh, wait a minute. Wait, did you? Uh-oh. This was not good. You guys don't turn these two lights on at the same time, I hope.
No.
No, something's going on here. Okay, so now I'm gonna give the fuller answer to the deferred question, like what's really going on with the exiting and the assisted. So the way Esterel looks at individual subcomputations is there's an ordering on how they possibly finish. They can compute a value, they can pause, they can compute a value which is smaller than pausing, which is smaller than exiting to a trap. Okay. And so what par does is it says, okay, just go. You two arms, just go. And when you're done, let me know. And then whichever one of you is the bigger one, that's the one that I'm going to do. The par itself is going to do. So in this case, the par here paused, and the par over here exited. So this arm of the par paused, and this arm of the par in the third instant exited. So the par just runs forward till it knows what the two things are going to do, and it's actually figured out this one's pausing and this one's exiting. And it's like, okay, so then I'm exiting. But the emission already happened before the pause. So that's why we have both red and green in this instance. And it all comes back to determinism. Okay? There's no other answer that makes sense from the perspective of we have to have a deterministic semantics. Well, it's not there's no other answer, but that's the root of the reason why it works the way it does. Is the rule for par has to sort of be deterministic. That's the final answer in your particular instance has to be deterministic. So you run forward until you know what the two arms are going to do, and then that par decides what it's going to do about that. And this is why it's important. There's no infinite loops anywhere. Like you don't want the par to wait forever. Right? Yeah.
So the key thing here seems to be that exit trap doesn't also pause, right? Like you don't pause when you do an exit trap. Like it exit traps and then continues.
Yeah, it's because exit is sort of bigger than pausing. It's sort of par is like, oh, okay, this exit doesn't really this pause is going to be kind of superseded. Mm-hmm. But because we want determinism, I have to actually run and let you get to that pause. Mm-hmm. So that's why we get the pause, we get the exit, and then after we've determined both of these are, then we're going to come down here to the sustain, mm-hmm. which means the emit happens, and then the whole thing actually pauses. So if we've been in some larger context where there was another exit, we would sort of be like, oh no, whoops, we're not actually going to pause. Off we go.
Is it a common pattern in Esterel to often have a pause immediately after a with trap?
It's more like, I don't want that anymore. Throw it away, I'm doing something else. And you could decide to be doing something else only in the next instant.
Right.
By putting a pause. But you could, we want to transition to green here.
Yeah, that's what I was thinking, is that I want to be doing something else is better supported by doing the pause, because the pause throws away all the signals that may or may not have been emitted so far, which helps me in a more sort of clean way understand that the next thing is starting from scratch, as opposed to starting from whatever else might have happened before I threw, because I didn't really throw it out from my intuition.
So I mean, you could say, like, you have to somehow do it like this, but this is not. So when you start composing kind of complex things, here we're just composing something that's emitting the same thing all day. But if we're composing something complex, maybe there's something else we want to be doing when we decided that we're done with it. We want to start something else or something like that. So that's why it's not baked in.
I definitely get it that exit trap is more primitive than exit trap plus pause.
Right.
Yeah.
And so in that spirit, there's actually one more thing of Esterel I have to show you, one more construct, and I'm not sure how I'm going to do on time here, but where what we'd really like to do is actually have it be green in the next in the same instant. So we want to, like, instead of waiting for green to the next instant, let's get rid of the red. Okay, so that there's one more construct. You can say suspend, and then what suspend means is when we begin the instant, if this value is true, like I'm going to put something here, it's going to compute something. If that computation works out to be true, we're just not going to do that. So it's a way of getting compositionality out of, like, this. Imagine this is a very simple thing, just because we can put it on the screen and understand it. But this could be some arbitrarily complicated, interesting process happening, having to do with landing gear. And we've decided now we're going to go around. So we want that, stop that thing and start doing something else, like putting it back up again into our airplane. Oh, Esterel, that's one of the big successes of Esterel. Airbus 330 landing gears implemented in Esterel. So we can sort of abort this complex thing and start our own new interesting other thing we're going to do over here. And we can suspend whatever this was happening, and then in parallel we're going to exit. So we don't just suspend it. This will just suspend it, but then this, because it exits the part, also kills it. That make sense?
So instead of a question mark, you can write a signal.
Yeah, you can put an expression.
But also just a signal, which means when the signal is emitted, then...
That's exactly what we're going to do. Exactly. So you have to say present. The signals are, you have to, like, pass it into the function, it turns it into a Boolean. Mm-hmm. So I'll make a, I can kind of see what I'm doing here, but not really. Okay, so if I do this, if I do this much, nothing will change. So I've made a local signal. This is making a signal whose scope is, these are global ones up here, but we make one that's just local to this spot. And then present, you pass in the signal, and then you get back the Boolean. Okay, so present, like, gives us back either true or false, depending on whether it's been emitted or not. And then now we're going to suspend this if this is present. So then I can just emit it over here, right before I exit the trap. And then that will turn the red off. Like this. Okay. So we didn't. That's the third instant. We get the green, the first one, because it emitted this S, which caused this thing to return true, which suspended that thing, and then we exited, and so the whole thing is gone now. So now we're just down here on the suspend green, but without having emitted red. Yeah.
So what happens if you write suspend, sustain, red, present, red?
Just wait. I don't know. I only have 5 minutes. What do we want to do? Okay. Yeah. So this question is kind of the reason why I spend all my time thinking about Esterel. So we have sort of with an extra 10 minutes or something past what our planned allotment, we could refactor this thing and actually make it a nice traffic light, and I could show you that maybe you can put 2 traffic lights, because one traffic light is kind of silly, you know, who are you waiting for exactly in the other direction? Okay, we can sort of make all that work out, and the first way we would try it we'd end up in exactly the situation you're asking about. Okay, so we'll just short circuit all that. But you saw how, like, we made a function and we called it. So we could take this whole thing and we could drop this into the body of some function, like the phase of a traffic light, phase light n, and like all this stuff will work fine if we sort of go through the details and work this out. I could type. So, you know, like all this kind of stuff is going to work out. If we sort of do this, and then we do, now we've abstracted over the redness, so we do red and orange and green, and we can, blah, blah, life would be good, we can have no traffic. Okay. Does that make sense to everybody? I don't know, maybe not, but you believe, because we have a couple of minutes. Okay, so what if we instead, let's make a new signal. Find signal. What am I? And then let's say I do if present. Oh, man. You can find a Wikipedia page on this code. There's a Wikipedia page dedicated to this code, believe it or not. Do you know what that Wikipedia's page name is? Let's look at the code, okay? I'll leave that as an idea, a question for you to think about. Let's look what the code is doing. It says, okay, so if what am I is present, if it, you know, and this will be true if what am I is emitted, right? And it will be false if what am I is not emitted. Right? That makes sense, right? Everybody, like, that's the point. We pulled the signal value into the programming language, so of course we can now put an if in there somewhere, right? And what you asked about is the much more sophisticated version of this program. It's the same phenomenon. Okay, it's gonna happen. So if it was emitted, this will be true if it's emitted. We'll just go to regular old if. Then we're not going to do anything. But if this is false, so if it wasn't emitted, then we're going to emit it. Think of the name of the Wikipedia page that is about this subject?
Process parallel.
The liar paradox is the one I was thinking about, but yeah, all the paradoxes I think are good here. Right. So okay. So any predictions about what Esterel thinks about these paradoxes?
Doesn't like them.
It must be an error. Right?
It doesn't like them. It must be an error. Yes, absolutely. Okay. The program is not constructive. Okay, what does that mean? Okay. So think of causality in like physics, right? What do you know about causality in physics? Like things have to be in the past in order to cause things that happen in the future, right? You can't go the other way. That's like causality. Okay, so this program violates causality. This program has no solution. You could say this program is like terrible. Okay, how about this program? Let's do this. Maybe I don't know which ones. I don't know what order is the best order. That's the least mind-bending to put these examples into. But like, let's look at this one for a minute. If what am I has been emitted, otherwise emitted. So it got emitted either way. Okay, so clearly we should be taking the true branch here, right? Like taking the false branch seems like a bad idea with this program, right? At least that. So okay, and if we don't want to take, if we want to take a branch, we've only got one left. If you take the false branch, then like you emitted something that this shouldn't have been false if you emitted it. Okay, so clearly you got to take the true branch here. No. Esterel doesn't like this program just the same because this program also violates causality. In other words, think of this as a cause, and then think of the way your branch goes, or just like getting about Boolean really as an effect. So all the causes have to precede all the effects. But here, this cause is clearly downstream of this effect, right? I mean, the conditional branch you have to determine the value of the conditional before you know which branch you're in. Yeah.
So if in the bar that starts on line 63, given parallelism, how do we know that the emit on line 67 happens before the present on line 64?
Because there is no time inside Esterel, is what Gérard Berry would say to you. Or another way to say it, this is a little bit less mystical, might be there's no causality dependency between the arms of a par. You have a causality dependency when control flow has to go a certain way. So you have to know whether this is true or false in order to get to one of these two. So that's like there's a causality dependency there. But when you have two things happening in parallel, there's no causality dependency. So Esterel just does them in the right order.
Is it the case that, like, in the Racket implementation, you could hit emit inside the body of sustain and later invalidate it because present the S gets emitted in the other thread?
No.
So it gets
and it's not about the Racket implementation. Well, I mean, I don't know exactly why you brought Racket implementation into this. So the different reasons you could have brought it into that question specifically. But like, let's say that there is a way to implement Esterel such that you don't have to do that. You don't have to. It doesn't. It's not. That's not what it's doing. Well, I should actually be a little bit careful about when I say that. The normal way you implement Esterel is you compile it to circuits and just wire them up in such a way that if your circuit has a kind of a bad loop in it, it'll crash. And if your circuit does not have a bad loop in it, you'll get the good thing happening. So you get a bad loop with this program. Yeah. As far as how you actually do that in the context of full-on Racket, continuations is the answer.
I have a different scheduling question that I'll save.
Yeah, but roughly what happens is the implementation, it says, okay, in order to go forward in this thread, just never mind, this is the only one thread, but in general, it says, like, I have to know what that is, and I don't know now, so I'll just wait. And then at some point, everybody's waiting for the value of something, and then you have to decide, something has to not be present here, or else this program is non-constructive.
Okay, so suspend is blocking until all other threads pause, or blocking until something.
Yeah, until something. Yeah.
Oh, seize and emit or all other threads. Okay. Okay.
For the present test specifically. This present is part of the Esterel implementation.
Block.
It's in on the game.
That completely answers.
Yeah, present blocks. But when does it know it can unblock? That's where you start seeing it real interesting. What's the rules? Yeah. And so roughly what it's doing is it's looking and trying to see if the program would have a causality violation or be non-constructive, and if it does, it signals an error, and if it doesn't, then it found something that didn't get emitted, so then it keeps going. Yep, that's the short route. Only 3 minutes over. Okay, well, that's Esterel. Yay.
Okay, thanks a lot. Questions? Mind completely bent. So you said it's the A something Airbus, whatever, the Boeing.
The A330 Airbus.
A330.
Yeah.
But only the
I
landing
flew
gear.
on when I came here, but unfortunately I was on a really hard Boeing with uncomfortable seats.
Only the landing gear part?
The landing gear lowering controller.
Okay.
And I haven't actually seen that myself, but I believe that's what I'm told.
Okay.
Yeah. So Esterel's niche is kind of safety critical systems because of this deterministic semantics.
Yeah.
And it has a deep connection through circuits to logic. So you can generate the circuit and then you can grovel over the circuit and analyze things about the circuit.
So you can basically build hardware out of
so you build the hardware directly from the circuit, and you can throw the circuit at an SMT solver and guarantee certain bad things don't happen in the circuit. So like with our traffic light, we might want to know that we don't simultaneously have a red and a green. So you can just make another thread that sits on the side, and if there's ever a red or green, you just be like, bad. And then you can throw this at SMT solver and say, bad never happens. And the SMT solver will be, yep, bad never happens.
Yeah.
And so it's a part of this safety critical validation world. Yeah.
Nice. Cool. So is that
here, none of that. Here, none of that. We've got full on Racket here, so there's none of that. But it's like the ideas about why you want to reason about your programs and why they work correctly. Maybe there's a way that's going to be useful for regular programmers too, not just people.
Yeah. So here you're using lang Racket, so Esterel here is kind of a library, or what?
Yeah, totally. It's absolutely a library. I mean, there's macros involved and whatever else, but you know, you could Esterel, pause, emit, present, par, with trap, with signal. These are all like constructs that are part of the Esterel language.
Yeah.
And it doesn't need to be a full language, so I don't need to have control of the entire program to implement it. Which is kind of the innovation that I'm going for here, and I have something that doesn't scale very well, but gets the right answers. So, okay, one problem at a time.
Cool.
Yeah. So like you can use regular old for loops, and it's fine. It's totally fine with that.
I think I was going in this direction because I would. So this is still, you can still like any Racket code and combine it with Esterel. So is this the idea, right? So this is not just an interpreter of Esterel.
No. This is real old Racket. You know, the chase scheme and everything, all that stuff running on there. So the trick is the continuations. So the implementation crucially uses full continuations internally. And roughly speaking, what it's doing is when all the threads are blocked on some signal that has not yet been emitted, and hopefully one of them never is going to be emitted, the continuations are used to kind of explore the future and find out. So that's why I wish I had to hedge on what you were saying.
So you actually evaluated then an else branches without knowing the result of present.
Correct. Yeah. Correct. And it's like, well, every which way I went,
Yep.
I get
There's paused, and I'm blocked on this thing, so.
Yep. And there's no there's no way to there's no signals I can set to false that will cause me to
Cool.
That's okay. I didn't say that quite right. That's not quite right. That's the idea. Yes.
Okay. Thanks a lot
Okay.
again to
Yeah,
both
thanks for
of
having
you.
me. Thank you.
And if you want to
Thanks for having
chat,
me.
just stick around.
Okay, great.